So in our last class meeting, we talked at length about how DC motors work. So today we're going to talk about their equivalent circuit model so that we can analyze things, as well as how they're typically connected. So a DC machine equivalent circuit looks something like this. So on the left-hand side over here, I'm going to put my stator circuit. Which is just some resistance RF. So this is representative of the resistance, the DC resistance of the field windings. And then we apply some field voltage VF, generating some field current IF. And so effectively, as I discussed previously, we have a simple electromagnet. On the right-hand side, I'm going to put the armature equivalent circuit, and I'm going to put a terminal here, A1, and then a terminal down here, A2. This black box right here is just representative of a brush. And then I'm going to draw a big circle. Like so. These terminals right here are the terminals across which I have my voltage VT. This current IA is the current flowing through the armature. And inside that big circle, I'm going to have my armature resistance, RA, and my induced voltage, EA. And we can simplify this representation down as follows. So instead of having that big, huge circle representing the armature and all that kind of stuff, we can just draw it like a normal circuit, right? So here's VF, IF, and RF. And I'm just going to put RA in series with my induced voltage EA. Here, this is my terminal voltage VT. Here's my armature current IA. And so this is, generally speaking, what we're dealing with in a DC generator. For a motor, let's see what's going on in chat here. Sean was asking if anyone else on Zoom can't hear anything. My microphone little light thing is showing up. And Lindy says that she can hear, so Sean, it apparently is just you. All right, so here's what our generator looks like. For a motor, it's effectively going to be the exact same circuit, except the only difference is that the direction of our armature current is going to be opposite, right? So I'll just sketch this up very quickly because that's the only change. So here's our resistance RF, our voltage VF, and our current IF. And then using the simplified representation, here's A1, A2 for our armature terminals, RA, BA like so. Our armature current is flowing in. And here is our terminal voltage. This is our motor representation, and just to be ludicrously clear about it, the only difference is the direction of current flow in the armature between these two equivalent circuits. So, using Kirchhoff's voltage law, the armature voltage EA can be expressed as the terminal voltage plus or minus the armature current times the armature resistance RA, where the plus sign here is used whenever we have a generator, and the minus sign here is used whenever we're dealing with a motor. Now, this armature resistance RA is actually several resistances that are lumped together. So RA is actually equal to the armature winding resistance RSE, the series field winding resistance, RCW, the commutation winding resistance, RCP, the compensation winding resistance, and REXT, which is just any external resistance that's in series with the armature. So we just lump literally all of those series resistances that are connected together in order to make the motor work, right? So series field winding, we talked about that earlier. That is, make sure I'm saying this correctly. A few turns of very thick wires connected in series with the armature circuit. So because it's very thick wires and it's only a few turns, that's going to be something that's very small. The commutation winding is all about making sure that the trailing edge of the brushes don't cause any arcing or anything like that. Compensation winding forms a similar role, and then the external resistance is just for biasing. So we just lump all of that stuff together and call it RA. All right, so our power and torque relationships are actually pretty darn easy for a DC machine. So what we're going to find is that the electrical power developed in the system must equal to the mechanical power developed in the system. So we can say that P electric and P mechanical are equal. Our electrical power developed in the system is just EA times IA. Our mechanical power developed in the system is just our torque times the speed at which our rotor rotates. And then we can set this equal to KA times phi D times omega M times IA, where this bit right here is just our relationship for EA that we developed in our last class meeting. So from this, we can simply divide our power relationship by omega M, sorry. No, that was right. Sorry. We can divide our power over our angular velocity and find that our torque is simply Ka, our coefficient, times phi d times Ia. So like I said, relationships for the DC motor, very, very simple. Okay. So a DC machine consists of two distinct circuits. We have our field circuit and our armature circuit, and the induced armature voltage EA depends on the flux per pole in the stator circuit. That's what that symbol phi D represents, okay? So because the flux passing through the stator depends on the field current, the induced voltage EA is related to the field current by the magnetization curve of the DC machine. So this is going all the way back to the stuff that we talked about at the very beginning of class, effectively magnetization curves for ferromagnetic materials. So what we should see is a curve that looks something like this. Here's our induced voltage EA on this axis. Here's our applied field current IF on this axis. And then we're going to have a magnetization curve that looks something like this. And it is at some particular speed. Again, this looks effectively identical to a BH curve for a magnetic material because that's exactly what it's representing. Okay. I'm sorry, what? Sure. So this magnetization curve data depends on the speed at which the motor is operated at. So if we were wanting to find what's going on at a different speed, we would actually need to make a pretty simple adjustment, okay? So our induced voltage at some speed 2, okay? So that's what that subscript 2 means. It's just at a different speed. Let me write that down here. So induced voltage at different speed than magnetization curve data. is going to be equal to simply omega M2 divided by omega M1 times EA1, where omega M2 is the speed that we're interested in, and omega M1 is the speed at which the data was collected, and EA1 is the induced voltage for a particular field current at the speed at which it was collected. So this is in terms of angular frequency. We can also put it in terms of our rotor speed as expressed in RPMs. So it's going to give us the exact same relationship, NM2 over NM1 times EA1. So that one single magnetization curve is all we would ever need to understand how it's going to operate for any field current and any speed. Okay. All right, so one of the last topics that I want to talk about is how we classify DC machines. So effectively, this boils down to the fact that the field circuit and the armature circuit of a DC machine can be connected in several different ways in order to produce different operating characteristics. So the first way that we're going to look at is what's called separately excited. So in a separately excited DC machine, effectively the field circuit and the armature circuit are excited by two different DC voltage sources. That's literally why it's called separately excited. Okay. So this connection is going to look something like this. We have a rheostat, and that is just a two-terminal variable resistance. This is the terminals of our field winding. So this is F1. Here's our stator resistance. This is our terminal F2. And effectively, we apply our DC voltage between these two terminals for our stator. Yes, so this is the shunt field winding. So let me put a note there. So there are two field windings, right? We have a shunt field winding and a series field winding. We're using the shunt field winding in this case. So that is what our stator circuit looks like. And then our armature circuit, I'll put over here. So here's A1, A2. We have that resistance RA, our induced voltage EA, like so. And then our terminal voltage out here. The next way that we could potentially connect things would be the self-excited shunt. And so effectively what we're going to be doing is we're just going to be connecting our field circuit in parallel to our armature circuit. That's all shunt really means. Okay. So that's going to look something like this. So let me draw the armature circuit first here. So here's A1, our resistance RA, our induced voltage EA, here's terminal A2. Bless you. Our terminal voltage. So our armature circuit is exactly the same, but now we are just going to take that stator circuit and effectively rotate it by 90 degrees and connect it. So here is our rheostat, RH. This is our shunt field winding. And we connect things like so. And this is terminal F1, and this is terminal effectively F2. Then we have self-excited series connection. And so in this case, we are going to connect the series field winding in series with the armature resistance. Okay. So if I put my armature circuit like so, here's EA, RA, armature terminal A1, armature terminal A2. This is RSE. So let me make a note here. This is the series field winding. This terminal S1 is the, and S2 are just for that winding. And then out over here, we have our terminals that our terminal voltage is applied to. VT like so. Then we have an option of a short shunt compound. And so effectively, that is the exact same thing as the self-excited series and the self-excited shunt at the same time. So starting with my armature circuit, I have something like this. I connect my series field winding in series. Here's my terminal voltage VT. And then I connect my field circuit in shunt or in parallel over here on the other side. And then lastly, we have the long shunt compound. So starting again with my armature circuit. Here's my series field winding. And my terminals. And now I'm going to, instead of connecting that field winding in shunt from directly across the armature terminals, I'm going to effectively feed this back around like so. So it's connected in parallel with the external terminals of the device as opposed to the armature terminals. So these are the different types of ways that we can connect the field windings, both series and shunt field windings and the armature windings together in order to get different types of things going on. So we're just going to look at a few different of these connections and develop some relationships on how the device is going to work. So let's look first at a few different DC generators. And let's start with a separately excited DC generator. So for this particular circuit, or for this particular type of generator, I'm going to have the following circuit. So I have my rheostat. Then I have my shunt field windings. This is the same circuit that we had earlier. I'm just rotating it effectively by 90 degrees. Here is my applied field voltage. Here is my field current. So that's my stator circuit. My armature circuit will be over here on the right. Here are my terminals. And across these terminals, I'm going to place some variable load resistance, RL, like so. And I'm going to put this little line right here. All this is representing effectively is my shaft that I am mechanically turning in order to induce a voltage. So the voltage drop across my load resistor is going to be simply VT. Here's my armature current, IA. So I'm going to call this voltage VA, which is the total voltage drop across my armature. And I have an associated current IA. This is the current IT that's leaving my terminals. Okay. And so we can just write pretty simple relationships for what's going on here, right? So on the stator side of things, our field voltage, VF, looks like it's just going to be our shunt field winding resistance plus our rheostat resistance times the current of IF. And we can lump those resistors together to just have a total field resistance of RF multiplied by our current of IF. So nothing more than application of Ohm's law there to get that going. Okay. Our induced voltage EA is just our terminal voltage VT plus IA times RA. So that's nothing more than Kirchhoff's voltage law around the armature circuit to figure that out. And we also know that our induced voltage EA is going to be KA times phi D times omega M. Our terminal voltage VT is just our terminal current IT times our load resistance RL. And by inspection, our current IA and our current IT must be the exact same things. So with these relationships, we can figure out any of the different quantities that are going on with our separately excited DC generator. Now let's look at a self-excited shunt generator. So just going to draw my circuit out here. RA and EA like so. This is my total armature voltage VA. This is my armature current IA. You may be asking yourself why I'm choosing to represent it here, so I'll explain that in a moment. Over here on the right-hand side, I'm going to connect my load resistance RL. Current flowing through my load resistance is my terminal current once again. The voltage drop across my load resistance is my terminal voltage. And then over here on this opposite side, I'm going to put my stator circuit. So here's my rheostat, my shunt field windings, excuse me. And I didn't give myself a whole heck of a lot of room here, but there's my shaft rotating at an angular velocity of omega m. All right, so one other thing I need to put here, there is my field current in its direction. So this one is a little bit harder to see what's going on, right? In this particular circuit, our armature current IA is not going to be equal to our terminal current IT because we can see that IF effectively takes away some current from our armature current, which is going to change some of the relationships pretty significantly, right? So writing a Kirchhoff's voltage law equation around, let me do it in this color. This loop gives us the relationship that our induced voltage EA is just going to be, once again, VT plus IA times RA, exactly like what we would expect for a generator, right? Well, our terminal voltage VT can be expressed by writing a KVL equation around this path. So effectively, the terminal voltage is just going to be the total voltage drop across the rheostat in our field or stator circuit and our shunt field windings. So that's going to look like our field current IF times our rheostat resistance plus our shunt field winding resistance, which we can express as IF times RF, like we did earlier. Applying Kirchhoff's current law, or actually, we could also say that our terminal voltage is IT times RL just by inspection. And Kirchhoff's current law tells us that our armature current is just our field current IF plus our terminal current IT. And once again, our induced voltage will always be given by Ka by D times omega M. So relationship's a little bit more difficult, but nothing too wild, nothing that Kirchhoff's current law and Kirchhoff's voltage law can't sort out, because it's just a simple DC circuit. And then lastly, for generators, we'll develop some equations for a self-excited series generator. So drawing my circuit out, I have A1, RA, EA, A2. My series field windings. This is my voltage VA. Here's my voltage VT. This is my current IA. This is my current IT. Here's my load resistance yet again. And figuring out things here should be a little bit easier than the last circuit. So we can see by inspection that IA and IT have to be the same current because it's just one big single loop, right? So IA must be the same as IT. My induced voltage EA here is going to be my terminal voltage VT plus my armature resistance and my series field winding resistance times my current IA. This will also be equal to Ka by D omega M. And my terminal voltage VT It's just IT times RL. So for these three generators, we can define our voltage regulation to be the percent voltage regulation is going to be EA minus our terminal voltage at full load. So effectively, our terminal current needs to be whatever the machine is rated for, and then whatever voltage we see across those terminals is the voltage that we use, divided by our full load terminal voltage times 100%. Our developed power PD can be expressed as simply EA times IA. Our developed torque is going to be given by PD divided by omega M, which is nothing more than EA IA over omega M, or KA by D times IA. And lastly, we can draw a quick and dirty power flow diagram. So over here on the left-hand side, we'll have our input, which is mechanical power, right? We are spinning our rotor and using this device as a generator. We're going to have some rotational losses. Oh, that looks terrible. So this is friction and windage and things like that. Here we have our developed power, so PD. Here we have armature copper loss and brush contact loss. At this stage, we're looking at our armature terminal power. So that's nothing more than, let's call it PA for the armature power, is just VA times IA. Here we have our series and shunt field losses. And then we have our output electrical power. Which is simply VT times IT. And we're going to go through effectively the same thing here for motors. So starting with our separately excited DC motor. Effectively, we're going to have the exact same circuit that we had earlier. Here's our rheostat, our shunt field windings, our current IF and our voltage VF. Over here is our armature circuit, A1, RA, EA, A2. Here's our shaft spinning at some angular frequency omega m. This time we are not going to load anything because we're not trying to get electrical power out, we're putting electrical power in. So our current is going to flow in the opposite direction through the armature. And then here's our terminal voltage. I'm going to do this in a different color to make this super obvious. So just trying to be explicitly clear here that we are applying power to the terminals in order to have this device work as a motor now. So our governing equations, the voltage drop across our field windings is going to be IF times our rheostat resistance plus our shunt winding resistance, which can once again be expressed as IF times RF. Our induced voltage EA is now going to be VT minus IA times RA, where the minus sign comes from the fact that our current is flowing in the opposite direction. And EA, as always, can be expressed as KA phi D omega M. For our self-excited shunt motor, drawing my circuit. So again, putting my input voltage source over here. Here's my rheostat and my shunt field windings. My field current IF. All right, so our induced voltage EA will be VT minus IA RA and KA phi D omega M. First relationship is just from doing Kirchhoff's voltage law around the right-hand loop. We can see, actually, I forgot to put it on here. My armature current IA is now going to be flowing down because the device is working as a motor instead of a generator. IA is given by Kirchhoff's current law, so that's just going to look like IT. Excuse me, that should be a T minus IF. just KCL at node A1. Our terminal voltage VT is just going to be the voltage drop across the rheostat and the shunt field windings. So that's going to look like IF times RRH plus RSH, or simply IF RF. And those are our relationships. And actually, let me do this on a new page. We're going to look at our self-excited series motor. RA, EA, A2. Here's our armature current, IA, RSE. Current IT. And my input voltage here, so it's obvious. Here's VT, and here is my shaft spinning at some angular frequency, omega m. All right, so governing equations, we have IT is equal to, that looked too much like an F for me. IT is equal to IA. EA is going to be equal to VT minus IA times RA plus RSE, which will also be equal to KA phi D omega M. I think that's the only thing that we really need. And then things that we might be interested in with regards to motors would be our speed regulation. So our percent speed regulation is going to be the speed at which our shaft turns under no load minus the speed at which our shaft turns under full load divided by the speed at which our shaft turns under full load times 100%. We can express this as angular frequencies or in RPMs. So N no load minus N full load divided by N full load times 100%. And then lastly, we can determine a relationship between speed and current. So we know that our induced voltage EA is KA phi D times omega M, which means omega M speed at which our shaft is turning can be got by EA divided by KA times phi D. And this will be equal to VT minus IA RA over KA phi D. And I'm going to separate this out as VT over KA phi D minus IA RA over KA phi D. And the reason why I split those up is because this term right here is actually our no load speed. And that's all I wanted to talk about. So I'm not feeling particularly great today, but there's going to be a homework assignment on DC motors, and so I thought we might just work some problems. Probably the homework assignment on DC motors. See what's going on in the chat thing here. Will you be able to have a formula sheet on this exam? Absolutely. In fact, you can just bring your notes and all that kind of stuff like the last test. My student worker is uploading the videos as we speak. I don't know. Probably. I don't think that she's going to do it, but I can do it tomorrow. Can you please send me an email to remind me to do it tomorrow morning? I'll try. You just keep sending me emails until I do it. How's that? At some point, I'll get annoyed enough to do my damn job, Bailey. I thought you guys said you wanted it on Thursday. Yeah. If I'm being honest, maybe I shouldn't record this, whatever. I don't have any particular preference, so it's not going to hurt my feelings if you want to. If you as an individual want to take it on Thursday, it will be ready for Thursday. If you as an individual want to take it on Tuesday, shoot me an email to let me know so that I know whether or not I need to come to campus on Tuesday to give you the test. I have no dog in that hunt. I don't have anything else better to do with my time, so yeah. Okay, well, like I said, shoot me an email or I'm gonna forget. Okay, so let's pull up the homework assignment that was from last year that I have no intention of changing because I'm tired. So 360. Homework set number 8. And then, oh, those are all open the folder, not rename it. All right, so this is the homework assignment that I developed last year for DC machines. So let's take a look at this thing right here. Problem 1 looks to be very similar to an example problem that we worked in class on last Thursday, so I figure we probably don't need to do something like that again. Problem 2, we're asked to determine the armature current, the developed power, the developed torque, and if the machine is acting as a motor or a generator. So that might be something interesting to figure out. So let's look here. So the machine is operating at a particular speed at a terminal voltage of 250. The armature winding has that many coils and that many turns, particular armature resistance. We're given the cross-sectional area of each pole face so that we can calculate the flux from that, blah, blah, blah. And then we're asked to determine the armature current, the developed power, the developed torque, and if the machine is acting as a motor or generator. Okay, so the only thing right off the top of my head that I'm not remembering exactly how to do here is actually to do the first part, the IA. So I'll think about that for a moment. Let's answer the last question first. Is the device acting as a motor or a generator? How do you think we might sort that out? So effectively, if the device is acting as a generator, the induced voltage EA should be larger than the terminal voltage VT, because we're going to see some losses in the armature resistance RA, right? So EA is 236.25 volts, and our terminal voltage is 250 volts, which means EA is smaller than VT, so this must be a motor. For our torque, that's just going to be power divided by our speed. So since we've surmised that this thing is acting as a motor and we're trying to find our armature current, let me cancel this out, right? We really only need, this is going to be problem 2. So we know that EA was 236.25 volts. VT was 250 volts. RA was 0.15 ohms. Anything else that we need from that? Omega M, no, NM was 1050 RPM. So because this device is acting as a motor, we figured that out. We know that EA should be VT minus IARA. Make sure I got the EA and VT on the right side of that equation. I did, okay. So that means that IA should be VT minus EA over RA, just by doing simple manipulation, right? So that's easy enough. For the second part, we are asked to determine the developed power. So our developed power relationship, going back to the fundamentals here, since we weren't told how this was connected, is simply EA times IA. And then our developed torque is just PD divided by omega M, which would be PD divided by NM times 2 pi over 60. I was trying to remember it was going to be 60 over 2 pi or 2 pi over 60, but I think it'll be this way. So pretty straightforward problem too. So let's look at what's going on here in problem 3. So problem 3, we're explicitly told that we have a separately excited DC machine, and we have a rated terminal voltage of 250 volts and a rated armature current of 100 amps. And it's operating at 1450 RPM. The total armature resistance is 0.129 ohms. If the machine is operating as a generator at full load, determine the induced armature voltage, the developed power, the developed torque, and the voltage regulation. Okay. So we've got a separately excited machine. Let's write some of this stuff down. Let's maybe throw some numbers at this. So VT rated was 250. IA rated was 100 amps. NM is 1450 RPMs. RA is 0.129 ohms. And we're asked for EA, PD, TD, and percent voltage regulation. And we're also told that it's a separately excited machine, right? So we go back up here to a separately excited generator. These are all of our relationships, right? We're told that the device is operating at full load, which means that VT is just going to be VT rated and IA is just going to be IA rated. So it seems to me like we would use this equation right here to solve for part A pretty much directly, because we have all of the constituent pieces of this equation, right? So knowing EA, VT, IA, and RA, it should be pretty easy for us to figure out our developed power, because that's just going to be EA times IA. Our torque would be EA times IA divided by omega. And then for our voltage regulation, that's the only thing that's not super obvious. So let's look here. When we have EA, we have VT at full load, which is just the rated terminal voltage. So we have everything for the percent voltage regulation as well. So it's really just now that we know how the machine is connected, which set of equations do we use to figure out all of the stuff and then come down to the bottom for the basic relationships. So problem three is also, I think, rather easy. In problem 4, similar thing, except that now the machine is being operated as a motor. Once again, it's a separately excited machine. So finding the exact same quantities except for part D, if we scroll down here to our DC motors, here is the relationship that I would use to solve for EA. EA times IA is my power. Divide that by omega M to find my torque, and then my speed regulation. I have VT, I have IA and RA, so I should be able to figure out what the product of KA and phi D is, and then use that to calculate omega no load, because I already have omega full load from the problem statement. And that's the homework set. Yes. Self-sided shunt motor. By the way, after class on last Thursday, I looked up how brushless work, and it's pretty interesting because it doesn't work anything like a normal DC motor at all. In a brushless DC motor, I might draw a picture here in a second after you get finished writing down whatever it is you're writing. It actually works very similarly to an electrostatically actuated MEMS motor that I looked at when I was in grad school. Let me scroll down here. So this would be characteristic of what's called an outrunner, brushless DC motor. And so I'm going to draw this the best way that I can. So I have typically six coils like so. They're connected in various different ways, so I'm not going to bother with that part. And this guy right here effectively forms the stator. And then outside of here is the rotor, and affixed to the rotor is a magnet. So we have a north pole here and a south pole here. So this is an interesting design in as much as the rotor is on the outside and the stator is on the inside. The rotor is still the spinning thing. There's going to be bearings and all of that kind of stuff. But effectively how it works is if you energize this coil right here and make it look like a south pole electric magnet, it's going to attract the north pole of the permanent magnet on the rotor. And then right before it gets there, you turn this coil off and then turn this coil on so that it keeps pulling it around and around and around. And the exact opposite thing is going on these guys down here. So we make this one look like a north pole when the other one looks like a south, just by winding it in the opposite direction. And so it's pulling it twice as hard because you have two of the coils doing the same thing. So all of the control comes from a MOSFET circuit that's just effectively an electronic speed controller. That all it's doing is switching the coils on and off at a particular rate, and it pulls the rotor along at that rate. So it's just dealing with magnetic attraction of opposite poles. So very, very different than a conventional DC motor. What are you talking about? We're gonna, the exam is going to be on synchronous machines and DC machines. You've had homeworks on synchronous machines and you're about to be assigned a homework on DC machines. I think so, yeah. There should have been 2 homework assignments on synchronous machines and then only this one on DC machines. Much like the other tests, it will be homework problems with change them. Yeah, so I think I combined all of the synchronous machine stuff into a single assignment instead of 2 assignments like I did last year or something like that, because I didn't put it up in a timely fashion or something because I got busy and tired.